like that, if
Right,
you
let
want to
me
ask a
see.
question, because I can't really see people like that. Yeah. Okay.
Just
Is
say
it
I've got to jump out at 30 minutes. Sorry, Neil, but
okay?
I can listen to the rest after.
Yeah, no problem. Thank you for coming. Is it recording, Leah? Has the recording started?
Yes, recording
Oh, okay,
started.
great.
Sorry, I was on mute. Yes, it is.
It's all right. There'll be that bit at the start. Going, is my microphone right? Okay. Anyway, right.
Great.
So, for those of you who don't know me, I guess I'm best to start by introducing myself. My name's Neil Carhart. I'm a civil engineer by background. I'm in the civil engineering department in the University of Bristol. I'm a lecturer in infrastructure systems. Hi, Jez. Um, So my research is into understanding complex infrastructure systems and systems approaches in general to the built environment. Um, as an introduction, the purpose of this webinar, kind of why because it felt useful, interesting to hold this webinar, was really to start a discussion about the use of systems approaches within the Trude project and how they might be of value to the Trude project and how we could best work together to try and extract that value from those systems approaches. And a bit more further context, I don't know the degree to which you can read these slides, how clear they're coming through, but the systems mapping element is in the proposal there in work pack 1, 3 and 4. But I don't think the systems approaches necessarily are limited to those, and they can cut across all the work packages. There are lots of different ways in which they could potentially be of value, and that discussion around how they might be used in those and how it might be beneficial to the project as a whole is something I think we'd like to start discussing today, kick off that kind of discussion. And just to kind of contextualize the kind of thinking around systems approaches in public health, I found this survey from this year about teaching system science to public health professionals. So it was a survey in North America, and it was highlighting things like systems thinking, as it says there, as a foundational competency of training programs in public health. Systems strategic thinking rated pretty highly in the US public health workforce survey. So there's quite a bit of thinking around the use of systems thinking and systems approaches in public health. I want to talk a little bit about what systems thinking is, what the systems approach is, whether that's different from systems thinking, those kinds of things. My slides are being a bit slow to move on. So generally what I'm going to cover over the next 20-25 minutes or so would be a kind of a brief overview of the systems approach. I'm going to look at some examples of system tools being applied in contexts kind of adjacent to the things that Trude is interested in. And then at the end, I've got some questions to pose and have some open discussion around the use of systems approaches in the Trude project. Hopefully that all makes sense. Now, the systems approach, systems thinking, systems tools, systems theory, systems science, all these kinds of things, it's nothing new. And I think to most people, probably it's actually quite an intuitive, natural way of thinking. It's kind of generally can be summed up kind of by this quote from Aristotle, that the whole is more than the sum of its parts, that things interact in various ways. They interact to produce kind of emergent properties. Those emergent properties produce a purpose. The nature of those interactions, the nature of the parts might depend on who's looking at the system and what particular bits they're seeing. The purpose of the system might depend on who's looking at them. The different people have different viewpoints on the system. But fundamentally, I guess the point is that systems is about the whole is more than the sum of its parts. How do we best understand the ways in which the parts work together to produce that moreness than the sum of its parts? And that's what kind of system tools and system science is, providing a toolbox of ways of doing that kind of thing. There's a lot of baggage with some of this terminology. So systems thinking is a term that you heard a lot to sum up that kind of philosophy of the whole being more than the sum of its parts. But when I'm discussing this with undergraduate engineers, sometimes it can be more useful to say, rather than get bogged down in any of that language, It's really about a philosophy, an approach to problems, and an approach to systems, kind of thinking about things as if they are systems, or thinking about things as if they are parts of bigger systems. And that's just a way of talking it without getting bogged down in the baggage of the terminology like systems thinking, system science. And that thinking about things as if they are systems does tend to come naturally to some people. We talk about economic systems, we can talk about environmental systems and man-made mechanical systems, and we talk about political systems. So we use the word like system all the time to refer to these things, and I think people intuitively know that when that word is used, it's talking about something which is made up of these different component parts, and they're interacting in various ways to bring about new behaviours, new capabilities, those kinds of things. And so the systems approaches are all about how do we understand those interactions and those parts. And you can see in these diagrams just different ways about how those things might start to get mapped out. These images are all kind of relatively informal approaches to mapping those things out, but the systems subject area has lots of formal ways as well for thinking about it. I think this book, Thinking in Systems, a Primer by Donella Meadows, is something I'd recommend people to, if you want an introduction to systems. And essentially, her philosophy in this can be summed up as saying there are no separate systems. The world is a continuum, but we're all about the way in which we approach problems is all about putting these boundaries on things. And that's nowhere probably more so than in academia, where we have separate buildings with separate departments in, and people sit behind closed, solid wooden doors in their offices looking at their own little bits. In industry, people seem to have transitioned to open plan offices and all those kinds of things, but we tend to break problems down into their little bits. That's what we're saying. So, and what's the problem with that? What's the underlying problem if you do that? Is that you never really get to the meat of the problem. So we use this term systems quite a lot. Everyone's talking about system, their boiler system, or the political system, or the economic system, but we never really get to a point where we're trying to understand what is that system, what does it really mean, what are its parts, how do those parts fit together. And this quote from Zed in the Art of Motorcycle Maintenance is kind of saying, if we want to change the system, we can't really do that unless we really understand how it works as a system, how all those parts interact with each other. If we don't do that and we try to impose challenges, then the underlying structure of the system is still there to reproduce itself in the same old way. So that's a kind of very brief overview of the systems approach. I'm going to go into a little bit more detail of that over the next 10 minutes. The other way of thinking can be summed up by this Cartesian reductionism. So René Descartes, he's the guy who said, to solve complex problems, what I do is I divide them up into their smaller little bits. I chop out a bit of the system, normally where we've got two variables that I can control one and monitor another one, and I'm going to take them away and study them in isolation. I'll change one and I'll see how it affects another one. And I kind of just assume that when I put all of those pairwise comparisons back together, it still works in the same way. Or I kind of just assume that when I take my experiment from the lab and I put it back into the complexity of the real world, it still works in the same way as it did when I was looking at it with these just two isolated bits in a lab. So those are two very different viewpoints, but they're not in competition with each other. I think it's very easy, particularly when I'm talking a lot about systems, to seem like I'm trying to put down that reductionist Cartesian way. Clearly, that's a very powerful, very important way of thinking about problems. And that's pretty much got us to where we are today. It's just that sometimes we hit problems that people see as being intractable that might be intractable because we're trying to apply these kinds of Cartesian ways of thinking about them. So they're really complementary. They're not in competition with one another. So we're all on the same page, and I know lots of people on this call will be familiar with systems, but just to make sure we're all on the same page, a system is generally defined as being a set of parts that are interconnected such that they produce properties or capabilities to serve a particular purpose that none of those parts could have served in isolation from one another. It's a very sort of straightforward definition of a system. As I'm saying, with that Cartesian stuff, the common methods for analysis, for problem solving, are all about separating the bits up into different topics, different subject areas, looking at them in isolation. And when we do that, we miss out these emergent properties that only appear when they're arranged in their particular context in a particular structure. And you see that naturally, I guess, when talking about biology. You take a body apart and it doesn't have the same properties or capabilities as when all those parts are interacting together in a context. You can see it in the kind of the urban built environment. If you take a city apart into its constituent parts, however you want to divide that up, and there are numerous ways in which you could do that, and it ceases to have those kinds of aspects that make it the city that it is. We see it in engineering, in man-made objects. So here's just a really clear example of that, where we've got two mobile phones, an old iPhone, the iPhone 10, and then the equivalent Samsung phone, the Galaxy S9. And if you look at that table at the top, you can see that if you split it down to its individual component parts, the Samsung phone is quantitatively better, all of the components that are put together to make that phone. It has a larger processor with more cores, it has more memory, it has a bigger battery capacity. It is more quantitatively in every dimension in terms of its component parts. But when you fit those together and you put them through standardized tests, you can see in the performance tests, the iPhone 10 is outstripping the Samsung phone. In video editing, the iPhone is able to do it much faster than the Samsung phone, and the Samsung phone's battery life is only slightly better than the iPhone. So when you put those things together, they can be put together in more optimal or less optimal ways. But if you took a simply reductionist view and just thought, if I pick the optimal components and assume they all work together as a system, then you don't necessarily get the best system. So that's kind of this whole thing of systems engineering, where we look at those sorts of things. And then in kind of the policy landscape, in economics, there are plenty of examples of policies in economics that aren't really looking at the full system or appreciating it. So some people might be familiar with the Cobra problem, which is this idea that a kind of apocryphal story that in India there's a problem with a population of cobras. So the policy intervention was to put a bounty on delivering dead cobras to the government. It worked in the short term, so the government was getting dead cobras delivered, they were paying out the bounty, the population of cobras in the wild was going down. But after time, it just started to creep back up again, and the wild cobra population went back to where it was before this policy had been brought in. So they cancelled the policy, and the population of wild cobras skyrocketed. And it turns out that people had been farming cobras in order to claim the bounty. And when there was no longer a financial reward for bringing them to the government, they just released their cobra farms back into the wild. So you get these kinds of policy kind of interventions that don't necessarily understand the kind of complex. Essentially, that's about how we think about systems, and it's also how we think about problems, that we tend to think about problems as being discrete. We think about, it's happening over here and it's not going to affect something that's happening somewhere else. It's a economic problem, it's not a health problem, or it's a political problem, it's not a social problem, but there's no real divisions. In reality, the world doesn't care about the kinds of divisions that academia or industry or government try to place on these kinds of things. And systems is really about trying to overcome some of those boundary problems. There are, what I'm going to show now is a selection of slides which are, I'm not expecting anyone to necessarily take a lot away from, except for this one thing, that there are many, many different types of systems approach. And within each of those different types of systems approaches, there are a whole range of different tools to consider. And the reason I say that is because in the policy and public health landscape, there are a handful of systems related tools that have really got a lot of attention. And they're the same tools that you see time and time again. And they're great tools, they're really useful and valuable tools, and it's obvious why those tools are being used. But I think it's important at the start of this project that we just keep in mind that there are, there's a whole toolbox of systems tools that could potentially be of value to this project. And we shouldn't just be using one of them because we've seen other people use it in the same way. So broadly speaking, if we were going to divide the systems science into two different branches, there's something called hard systems thinking and there's something called soft systems thinking. And hard systems thinking tends to be applied to complicated systems. Things like an automobile or a mobile phone might be thought of as a hard system. It's complicated, it has lots of different parts, and we engineer them so that all those parts work together. But we can kind of predict how those parts are going to work together. And then there are complex problems and complex systems. And actually, it can be really hard to model those. And so we don't model them in a way that we're suggesting that the model is the real system. It's the map is not the territory. It's a way to help us understand it. It's a way to help us navigate the complexity. It's a way to help us manage that system and make it try to improve the problem situation, not try to resolve it. And that whole branch is kind of soft systems thinking. Sometimes people think about soft systems thinking as just involving people, but technically it's not that. It's about the complexity of the problem that it's trying to address. Some of you may have seen this. Again, I'm not expecting anyone to take loads away from this. I don't think you can probably make out the text quite that much. But really, I'm just saying that complexity sciences, system sciences, have this long history, and there's all kinds of different branches, and within them, all kinds of different tools. And we shouldn't, narrow ourselves down to those. But to give a very potted history, it kind of starts in the 1940s, 1950s. Things like cybernetics, which is this guy Norbert Wiener, who's looking at the way in which biological systems control variability within them. How do they deal with the variability of the natural environment? How do they become resilient to survive? And he's trying to mimic those in electronic systems. So he comes up with this field of cybernetics, of control and communication in machines. That inspires, he works with a whole group of people like Alan Turing, Gray Walter, who was based at the University of Bristol. He's credited with inventing the first AI, which is this thing called a tortoise. And if you go to the robotics lab in Bristol, they have a version of that. He wrote this book, The Living Brain. Ludwig von Bertalanffy created something called general systems theory. He's a biologist, and he's trying to come up with systems theory applied to biology. Gregory Bateson is doing it in terms of ecology. Jay Forrester is doing it in terms of, well, I'll come back to Jay Forrester, and I'll come back to Stafford Beer in a minute. But there's this whole range of people doing stuff, and they're all coming out with different tools. And another way of dividing up those tools might be to think about hard systems thinking, soft systems thinking. Then there's postmodern systems thinking, and there's emancipatory systems thinking, for where people see systems as just reinforcing power and control, and how can we use system tools to kind of break down those power and control structures. And within those, then you start to see these different tools. This is just some of those tools. And I've highlighted in red system dynamics and soft systems methodology. Those are the two tools that you see most referenced in the policy and public health literature in the context of systems. So when people talk about systems used in this context, they tend to be talking about those two tools, largely speaking. There are a few others that creep in. I'll skip this, but this is a really great book about systems thinking and public policy. And I think the main takeaway from it is that it's talking about this thinking about things as if they are systems rather than as discrete components to be engineered and tweaked in isolation from one another. And this idea of trying to solve problems from the bottom up. So rather than imposing an idea of the system from the top down, actually working from the bottom up to understand the components of the system, how they work together, and how they work together to produce things that emerge at the higher levels. Similarly, in urban and regional planning, or in urban planning, there's probably a longer history. This is a good book by Brian McLaughlin, which is looking at systems approaches as applied to urban planning from 1969. So a longer history there, but it's a good book for providing an overview of systems and contextualizing it in the kind of built environment space. And then if you scale that up to the whole sort of national level, there's something called Project CyberSyn, which was imposed in Chile in the early 1970s by Stafford Beer, who's a British cybernetics expert. And he created this systems model of the whole of Chile, its economy, its political system, its industries, its social systems. And he built this model. This is a real control room that they had in Chile. And for a few years, they controlled their whole country using this systems model, this cybernetic system, so that it would kind of almost govern itself. And then there was a revolution and it kind of stopped. But it's a really interesting case study of using systems to manage complexity of an entire country. And then here's another book I'd recommend for an overview of systems approaches in population health. And again, it's saying exactly the same thing as in this introduction. We're used to breaking things down into smaller parts, but actually we can view these problems as complex, as being connected to one another, and the systems sciences, systems thinking, systems approaches as a toolbox to help us to do that. And it can be really useful, I think, to also acknowledge where there are problems that are tame or simple or easy to deal with, where systems tools may be overkill, and where there are wicked problems which are categorized by complexity and uncertainty, potentially, aleatory uncertainty, randomness in the system, where actually it's really difficult to determine exactly what's happening. The system is so complex we can't know the connections between cause and effect, and they might be producing these kinds of emergent random properties. And it's at that end, that hard kind of wicked end, where systems approaches are really valuable. Applying them at the tame end can be a bit overkill. People sometimes criticize systems as being formalized common sense. And I think that is when people are trying to apply it to those kinds of simple problems where actually you don't need to apply it to those kinds of problems. And if we build these kinds of models, the value that they're offering, I suppose, really is to get a shared understanding of how these systems works. And ultimately, they've been used to identify levers within the system that can be pulled, that can be changed, that can be tweaked. And we can use those models to track through cause and effect, to perhaps run simulations, to see how those changes might propagate out through a complex system. So some examples of tools, again, very briefly, I know I'm rattling through this, but I want to leave time for discussion. Like I said, there's a whole range of tools then associated with this philosophical view that the whole is more than the sum of its parts. In hard systems engineering, there's a lot of stuff around stakeholder mapping, requirements analysis, trying to understand what it is that end users really want from these systems and how we use that information to then design and build man-made systems to fulfill those needs. Related to those kind of hard systems engineering problems are things like functional block flow diagrams, which map out the components of the system, the functions they perform, and how they all fit together. Design structure matrices or n-squared diagrams, which are looking at interactions between components. Swim lane process diagrams, which are looking at actions and steps in a process and when they all take place, who they're being, who's taking those decisions, what information they're using. So there's all these kinds of different tools. But predominantly the one you tend to see, maybe because of the work that was done on these obesity maps, is system dynamics and causal loop modeling. So many of you, if not all of you, will have seen these kinds of things before, I guess, but they're these very messy spaghetti-looking diagrams that are trying to map out the entire system. This one is looking at obesity and food consumption, food production. You can see each of the boxes is a kind of variable that is involved in that problem, and each of the arrows represents a cause and effect relationship between those variables. So we can look at which of these variables could we actually do something about, and if we did target it and change it, how would that propagate out through this system? There may be different feedback loops in there that may, like the Cobra problem, may actually make that intervention ineffective, may actually bring about a worse situation. There may be feedback loops in there that have a reinforcing effect. So if we make a small change, it actually amplifies to make a much bigger change. And this is linked to something in systems, but I'm sure it's not exclusive to systems, of the iceberg model, where people talk about events at the top that we kind of see that are very visible to us, and those events are products of longer term patterns of behavior, and those patterns of behavior are created by underlying systemic structures. And if we want to make long term lasting sustainable changes, we need to target the systemic structure that is creating the patterns of behavior, that is creating the events. But we can often get bogged down in firefighting, in targeting events, focusing on events. What's the next event? Sometimes we do think about longer term patterns of behavior, but it's less common to be really thinking about the systemic structure that brought about the behavior, that brought about the end result, whether we wanted it or not. So we have to think about, how do we understand these systemic structures? And system dynamics and causal loop modeling are really about trying to understand those systemic structures. It was created by this guy, Jay Forrester, who I mentioned previously at MIT. He first applied it to industrial processes, so he was modeling factories using this causal loop and system dynamics modeling approach. That had some success, so he was approached by some various cities and urban planners to try and model a city, scale it up from the factory level to the city level using his modeling approach. So he wrote a book in the early 1960s called Urban Dynamics, which talks about those models. That was then taken up by the Club of Rome in the 1970s, who commissioned him and his group at MIT to model the entire world using their approach. They produced a book called The Limits to Growth, which built a model of the world which looks like this. It doesn't have a huge number of variables in it, but it's a system dynamics model made up of stocks and flows, variables with feedback loops and cause and effect relationships mapped out with arrows. You put some data in that, you can simulate it, and you start to get plots of basically what those variables are going to do, projecting into the future. This was published in Playboy. I've actually taken this article from the 1970s about their work. It was pretty influential in the sort of ecological movement, but it was seen as maybe being a little bit too aligned with the political motives at the time and being used to actually control people rather than actually improve any kind of environmental outcomes. But they were kind of predicting with these models that you might see ecological collapse around the middle of this century, kind of 2050. And what they sort of show in those models is you can put tons of data in. There's so many uncertainties. You put loads of uncertainties in. You run thousands and thousands of iterations through some Monte Carlo simulation. And regardless of the data you put in, regardless of the relationships, the structure of the system still causes you to see collapse around the same sort of time. So actually, it doesn't matter how robust or rigorous we are in that data. If the structure of the system is modeled correctly, it seems to suggest we're still going to see that kind of collapse because those feedback loops are always going to incentivize that kind of unhelpful behavior that brings about collapse. They're really simple models to build, actually, causal loop models, and it's probably another one of the reasons why you see them used so much. So because they're really based around just two different types of arrow. An arrow where you have a positive causal relationship, so it's saying we've got two variables, A and B, and an arrow with a plus at the head would mean that as variable A changes, it causes variable B to change in the same direction. So as variable A decreases, it causes variable B to decrease. And as variable A increases, it causes variable B to increase. And then you have a red arrow or an arrow with a negative sign at the head, and that means there's an inverse relationship. So any change in the parent variable causes the child variable to change in the opposite direction. And you can use that to build up these kinds of models where we have variables. Here's a simple example. Eggs and chickens are our two variables. As the number of eggs increases, it causes the number of chickens to increase. As the number of chickens increases, it causes the number of eggs to increase. We get a reinforcing feedback loop there on that side. If nothing else is changed or happening in that model, if we just introduce some eggs, some fertilized eggs presumably, then the number of chickens is just going to increase, and that'll increase the number of eggs, and exponentially they both increase. If we think about road crossings and assume chickens like crossing roads, but they're not very good at crossing roads, then as the population of chickens increases, the number of road crossings we count goes up, and as the number of road crossings goes up, the number of chickens goes down, so that's a balancing loop, and that's trying to resist change. It's trying to keep that chicken population stable. So if we didn't know that balancing loop existed and our policy intervention was just to introduce more eggs into the system to try and get the chicken population up, it might work in the short term, but in the long term, that balancing loop would try and work against it. So these models are there to try and help us understand where these kinds of structures that produce these dynamics exist in the system. And like I say, they're very widely used. These foresight obesity maps, I've used them to try and look at all the different factors involved in obesity, the obesity problem. There's some links here that people could see, can look at afterwards if you're interested. This is a system dynamics model of the COVID-19 spread issue. So you've got stocks there of people and all the different variables like urban density. You can put data into these models. This online version of the model allows you to change all of your assumptions. So you can change it to look how infective is the disease, what's the urban density. You can change all those variables. You can put uncertainty parameters on them. You can run simulations, and you can start to see what the kind of outcomes and projections might be. So there's some examples there if people want to look at them later. But really it is all about the fact that these underlying structures and that COBRA problem is a specific type of problem, which in the system science, people have identified archetypal failure structures. And wherever these structures exist, systems tend to fail for the same reasons. So this one is an archetype called fixes that fail. The COBRA problem is a specific example of that. You've got a problem. The more of the problem you have, the more of the fix you put in place. The more of the fix, the less of the problem. Great, that's what we want. But if the fix has an unintended consequence, and the more of the fix you put in place, the more unintended consequence there is, And the more unintended consequence there is, the more of the problem there is, then you have this reinforcing loop, which is also acting there. So that fix may not be the best fix because it has this unintended consequence. How do you build these models? How might we be able to use them in Trude? Well, we could have facilitated workshops to help people build them. We've done these. Here's one that was led by a colleague with Bristol City Council looking at air quality. So the whole group of people, sometimes called participatory model building, gets around a whiteboard, post-it notes, tries to sketch out one of these causal loop models. You can kind of clean them up a bit in a computer and you end up with fragments of them that look like this. We've got all the variables and the feedback loops involved. You can then use it to work out what your policy interventions are going to be. So these are all the factors or some of the factors involved in air quality in Bristol. You can start to think about introducing interventions like encouraging walking, congestion charging, and you can track how they might affect the system, and you can make it cybernetic so it controls itself. So you can actually link all of those things to air quality, a bit like a thermostat. So congestion charging is dynamically controlled by the air quality. Or if it's not possible to do group model building, participatory model building, we've actually got experience of producing maps from documents and interview transcripts. So take an interview transcript, you just look for words and terminology that means those kinds of cause and effect things. So here's a piece of text, simple search through in vivo or whatever it might be to look at words like because, therefore, as a result of, all those sorts of things. And you can start to use it to create these kinds of models and extract them from those transcripts. Soft systems methodology is another one you popularly see. It's all about saying people have different views on a complex problem. We need to extract their mental models of the world, combine those mental models into some new collective shared model, use that shared model to diagnose what's wrong with the system, test that back through the experts, and then implement it in the real world. It's generally associated with things like rich pictures. So to try and get a shared mental model, very informal way of getting people to talk about what are all the problems in this situation. Essentially, it's just a picture, that people sketch out. It looks like something like this, where people are trying to say, what are all the factors involved in this system? What's going on? Who's in conflict? What are the things people value? What do they want? What don't they want? And then using that to come up with a root definition of the problem, thinking about who benefits from it, who's going to perform the system's activities, what does the system actually do, what makes it a valuable system, who owns the system, what's the context for it. So coming up with a root definition is also another component of soft systems methodology you see a lot. Agent-based modeling is another tool that you sometimes see. So here's an example of one we built looking at the flow of people in emergency scenarios around Bristol. So you identify all the different people, you give them little decision trees, you work out what's important to them, by asking them. Obviously, you work with them to get this information, find out what's important, how they make decisions. Every single individual agent then has a different rule set, different things that are important to them. And you run simulations to see how people are going to flow through a city or a system. So we can do agent-based modeling. Bayesian belief networks is another one you sometimes see. So a Bayesian belief network uses Bayesian probability to kind of piece together partial information to work out the state of something that we really can't directly observe. So we build these networks of cause and effect, and we start trying to populate them with pieces of information that we do have access to, and we can from that extrapolate the state of things, the likely state of things that we don't have direct sight of. Troubleshooting software or diagnostic software will use Bayesian belief networks. It will ask you questions about the state of whatever the system is you're trying to diagnose. And from all that information, it will piece together a picture of trying to say what's actually wrong with this system. And then in the hard systems side, there's this whole field of systems engineering, which is a toolbox full of many, many different tools. Essentially, systems engineering is saying the systems we're dealing with are too complex that any one model of this system is going to give us a sufficient picture of it. So we need multiple different models. And if we have multiple different models, we need to know how those models talk to each other in a consistent way. So, for example, in the architecture of a building, you will have lots of different models of that building, physical models, 3D models, structural models, elevations and plans, bills of materials. They should all be coherent and consistent. So we have all these models and then we have an ecosystem that fits them all together. If it's really complex, you end up with something like this. Now, this isn't actually a model of the National Airspace System. this is a model that tells you what each of the models that make up the architecture of the system is. So each of those little boxes is just another document with another model in it in its own right. And this is just the meta model that tells you how all of those models fit together. We have various tools like n-squared charts, which Jez and I have used quite a lot to look at infrastructure interdependencies. These swim lane diagrams I mentioned for looking at when things happen and by who and where. Quality function deployment is a way at looking at how soft aspects of the system map onto hard aspects of the system. So this is something that a student of mine did, looking at high-rise buildings for student accommodation, and then looking at the factors down in the rows are factors that affect student well-being and mental health. And the factors in the columns are decision points that civil engineers make, and they're looking at how those decisions map onto whether they improve or are a disbenefit to those factors of mental health and well-being. Functional block flow diagrams are mentioned. There's a standardized way of doing those using UML in systems engineering. So you can map out healthcare services, as this model is doing, using UML, decision-making processes using UML, as this one is doing. But essentially, what that whistle-stop tool was saying is there are lots of tools to use. Rich pictures, soft systems methodology, causal loop diagrams are the ones you see the most, and we could definitely use those in Trude, but there's a whole load of other things that we could potentially use that in the system center and perhaps through the rest of the project other people involved have experience of. So it might be worth discussing those as well. So that was actually about 35 minutes, sorry about that. But that was the very, very quick whistle-stop tour of the systems approach. What I wanted to do was just give you an idea that it is a very broad subject area with lots and lots of tools we could potentially use, but underneath it all is this philosophy that the whole is more than the sum of its parts, that we need to understand how all the different parts interact with one another. And I think that's that's good enough starting point for us. So before I prompt some discussion questions, does anyone have any questions, or is there anything for open discussion that anyone would like to talk about, or is everyone just a bit overwhelmed? I know it was a bit quick and a lot. If anyone's talking, they have their microphone muted.
Thanks for that, Neil. I think that was very good.
Does anyone have any particular questions? Or
Daniel, thanks a lot. It's very interesting. And I'm glad that at least some of the publication you mentioned I did read, especially the Brian McLaughlin one. That is a student set text, and he's from Manchester. I just say that for those who are interested in the more modern version, I think Michael Betty's work is very good. And yeah, the new science of cities and things like that. I think it's also quite easy to read. So that might be something that people can also follow it.
Yeah, definitely. I agree, yeah.
Neil, I don't know if you can see me. It's Sarah. I have a comment. I mean, there was so much there to take away. Thank you so much. It was very helpful indeed. And I think there's some really helpful meshes between your world and my world. But there's lots that struck me. But one point I'd like to make, which was how you referred to hard and soft system tools. And I think that's going to be particularly relevant for us with our different disciplines. So as you were speaking, I was thinking that perhaps some of our health colleagues come from perhaps the hard system world, where they're going to want to know about the evidence and the facts and the interventions and the evidence of impact. Whereas I like to think of myself as part of the softer system, which is about values and beliefs and informality. And I think it's going to be a real interest, but also challenge for the project team to mesh those different worlds. You know, we can use the soft to inform our understanding about how the system works, but what we are really going to be judged on by MRC is the hard science stuff. And I think that's a challenge that was going through my mind as you were speaking. So thank you for raising that.
That's good. I agree. I think there's this, one of the diagrams I showed early on is there is this pluralist movement down the middle of soft OR, soft cybernetics, soft system dynamics, which is trying to take systems approaches which are classically in that functionalist hard domain. I mean, how do you actually translate them to deal with some of the value-based complexity issues from that are associated with the sort of soft systems classically view? So I think there is academically there's a good valley of stuff in there as well to bridge those two bits, I think.
This is Kathy here. I don't know if you can see my picture.
I can now, yeah.
Okay. So couple of things, very interesting, really interesting. And some of the particular examples, I can see having relevance for, all sorts of applications in Trude. The couple of questions, though, I mean, really one is that in the research we do in real estate and planning, because we very much cross that divide between quantitative and qualitative, there's a constant tension between wanting to dig down into the soft aspects of any real estate and planning topic, and the requirement for hard evidence if you want to in any way quantify or monetize what you're finding, and a real challenge around incorporating the two kinds of data. That's the first one. And the other one is that in my experience, there's also an issue with predictive modeling. By the way, I was a student in the days when the systems modeling, Brian McLaughlin was, one of the set texts still. And of course, it did come in for very heavy criticism from urban planners. But, a problem I've actually experienced in practice and research is around predictive modeling due to the problem of missing variables, the fact that you can't really allow for technological innovation, and it's very difficult also to allow for unpredictable human behavior. So it seems to me that those might be some tensions that we'll experience, very much, talking to what Sarah just said, some tensions that we might have to experience with this project.
Yeah, no, I totally agree with all those points. I think that's a very astute observation. I think those things are a lot of these models. Thinking of the limits to growth, the Club of Rome model, World 2 model is, about how far ahead can you realistically predict. It can't account for any kind of, like you said, technology interventions. It can't account for policy changes. It can't account for people changing their behaviours. We've done a lot of work using these kinds of models, looking at safety culture and health and safety in safety critical industries, so particularly in nuclear and oil and gas, big process industries, and building these models to understand the socio-technical systems, so how people interact with the hard physical systems, and whether those things bring about healthy behaviours, safe behaviours, or unhealthy or unsafe behaviours, and using these models to understand them. And one of the challenges that we've come up with there is that sometimes as soon as you map out one of these causal loop models and you present it to a workforce, you haven't, I'm not advocating academics do in isolation, which we've built them with the workforce. So we've done participatory model building and they've built these models essentially, we've just facilitated it. And you reflect it back to them and they go, oh yeah, I can see how that's not helpful. So actually just being presented with the model means that they've now completely undermined the model, because all of the assumptions about how they would behave and what they think has now been changed by just seeing the model and the process of being built in. So there's a whole school of thought within system dynamics and causal loop modeling about two of these things. One, that you can't really use them for prediction at all. They're not robust enough for doing that. And secondly, there's this school of thought which is very functionalist, which says you don't include any of the soft variables. You don't include anything relating to values or people or policy. You stick purely to the things you can robustly quantify. But then the opponents to that will say, if you don't include people's values, then you're essentially saying they're not important, which is clearly wrong, or you're saying that they're taking a value of 0 to 1, or an extreme value that your model is, however your model is set up, and that's clearly wrong too. So there really is this tension in the modeling community for these systems tools is how to overcome some of those challenges. But I think it is definitely going to be at the crux of the problems we face.
So just to say that I think I mentioned in an email that I had a try at thinking about how complexity theory and modelling could be applied to looking at the complications of thinking about urban density. And it was a very, very shallow, uninformed look at it. That wasn't me sneezing. And but what did come from thinking about it quite as deeply as I was able to, with little knowledge of complexity theory and modelling, was that there were some aspects, and some of them you referred to, like the use of feedback loops, which, even if it's not very accurate for predictive modelling, make it incredibly useful for visualising the state of play as it is, and therefore for informing policy agendas, thinking about how relationships and associations between different factors can lead to potential crises, which would then need some adjustment of policy. So I think for me, I found that the value of it as a descriptive tool was, you couldn't really fault it on that, even if the predictive side of it seemed weaker.
Yeah, I think I'd fall down on the same side with that. I think as a descriptive tool, as a way of thinking through how these things work, as a tool on this kind of the soft system side of being a tool to help us understand the system, I think there's some real value in there. I think the reason that causal loop models have such a lot of use in this area is kind of thinking about, well, if your system is a room with a feedback loop in it, like a thermostat, for example, and you're trying to keep the room at a level temperature, and the thermostat is doing that work, and you ignore feedback. All of your thought processes are linear, and you ignore that the system maybe built out these feedback loops. So you're ignoring the thermostat in the room. Your intervention, your policy might be to open the window or turn down the radiator, but neither of those interventions will work because the thermostat will just kick in and try and up the output of the radiators more. You open a window, the temperature of the radiator is just going to go down. You turn the radiator down, it's just going to stay on for longer. So ignoring that feedback in the system can lead to ineffective policy interventions, but just being able to map it out to see that feedback exists can be useful. And the flip side of that is that the thermostat is a policy intervention. It is a way of getting that system to be self-governing. So actually thinking about feedback loops can open up a whole new avenue of potential interventions into the system to help it to govern itself and keep it sustainable. But it could just be just as a tool for thinking through things as if they are systems or part of systems.
Can I ask a question? Because I just thinking about Sarah's comment and then Kathy's comment. I wonder how much will be like when we do the qualitative work, do the consultation and understand the values and norms, and that will go to fit into the model to create different scenarios. And then those scenarios can go back to consult with the policymaker and the participant to get more information. So more iterative between the qualitative and the quantitative. And the modeling will not be one single answer. It may be a range of scenarios based on different value system.
Yeah, I agree. I think it's one tool in a toolbox. It can help us understand some things. It can. I think iteration is definitely going to be a key thing here in gathering some information, building these models. Models might just present different questions that haven't been thought of before that inform the next phases. I mean, that might be the value that they add is asking those new questions or highlighting new potential questions.
Neil?
Yeah.
Sorry, it's Andy Gibson here. I'm leading the public involvement in the project. I just wondered, how do systems cope with conflict, in the sense that I've listened to you talking about feedback loops. It strikes me, particularly in the urban planning thing, that there are actually people that are actively working in the opposite direction. So some bits of the system are actually working to undermine other bits of the system. It's one thing to assume that everybody's working together, but there might be things that people have misunderstood or feedback loops that people have missed or whatever, which frustrate their planning. But there's a second thing, which is what happens when there are sections of the system actually working to undermine or prevent other bits of the system doing what's achieved. And how do you model that kind of a problem?
Yeah, that's definitely another good observation, I think, and those things definitely exist. And it's perfectly possible to model those things in system dynamics, where variables and incentives and beliefs and values are working against others. I'm talking specifically about using system dynamics now, you can definitely capture those different things where you have different conflicting regulators, by which I mean regulators in its kind of system sense, not regulators as in a political or industrial sense. But really then it does come down to having to introduce a degree of quantification in the model to look at the strength of those influences if you wanted to simulate it. But there's a whole school of thought of not actually even bothering to simulate these models because the trustworthiness of the predictions is so low that what you really just want to do is just to use the model to really make the assumptions that people have about the system really, really explicit. So particularly if we do participatory model building and we get those people in a room, they may very well have very different values which put them in conflict with one another, and they want very different outcomes. But just recognizing that can be the first step, and the system can actually help people to see that they may want the same things, they just want it through different ways, and they can explore where those means might be compatible. But really, I think I see some of these things around causal loop modeling as being more about facilitating that dialogue to help people to have those decisions. I'm not trying to fix that problem, maybe trying to make that problem situation better, and that might be through using these tools to facilitate that dialogue. There are some specific examples I'm thinking of where there are these conflicts, and it tends to be what we find actually is that people have very different assumptions about the purpose of the system. So actually they kind of want the same thing, they just don't necessarily have the same mental models about how the system works and what the system should be doing. And some of these tools like Rich Pictures, CatWo, causal loop models can help people to visualize those models, those mental models, which would otherwise be tacit. And that can help as well. Sometimes, people don't necessarily disagree, they just understand the system in a very different way, and they're sort of pulling it in different directions because they have different understanding about how it works. Things like the justice system, for example, would be a clear example, which is people don't necessarily understand how the prison system works, but some people think it's about retribution, some people think it's about punishment, some people think it's about protecting the rest of society from the criminal element, some people think it's about rehabilitation. Those are very different purposes being placed on the same system. And so conflicts can emerge because people see different outcomes and different purposes from it. And is there a way you could re-engineer that system to meet all of those outcomes? Probably not. But you could at least have that discussion if you can front end those disagreements and the real mental models that sit beneath those disagreements and cause people to pull in opposite directions. Yeah, and I think that's where some of these tools could help. It's just mapping those things out.
Yeah,
Neil.
Thank you.
Hi, Neil. Jez here. Just thinking about how this will relate and might play out in the project. And I guess it sort of then goes over to the interviewing, Sarah, and the sorts of things that you might be thinking about. Are there any, so it's a sort of bit of a question really just to get us to think about that and when going off and doing the interviewing. So you showed an example text and the sorts of words that said this leads on to this and as a consequence that. So the sorts of words that lead people to talk about connections and interconnectivity. Are there particular things that you would want to do to kind of shape how interviews might be done, how the data collection might be done, those sorts of discussions? I think that might be an interesting area to pursue at some point.
Yeah, I think it's something for a collaborative discussion on the detail of how these things might get operationalized. I think if there's potential for iteration, that would be ideal. If there's a very light touch in any initial wave of interviews, which could essentially be just be aware of these kinds of causal words, just pick up on them. You don't change the questions in any way or the way that anything is asked. Just be aware that when people say these kinds of words, how that might translate into a causal loop model. And some of the stuff we've done before is kind of asynchronous participatory model building, which is where you use those transcripts to produce a kind of draft models, and then you have maybe gather a set of people together to go through those models and then refine them. And so that kind of is a way to not impose too much on the interviewing techniques. I mean, the absolute ideal, I suppose, would be to go in with a causal loop, with a blank whiteboard and draw a causal loop model with someone. But that means that other avenues aren't there, are then closed off, that people might want to ask questions about. So I think there is a discussion to be had maybe about how we best how we might make sure that none of the avenues are closed off. We aren't doing anything that's actually stopping something from being used.
And perhaps also identifying where there may be connectivity in the future, I suppose, because that's where it then leads on to Dan's area around interventions, because you mentioned that as well.
Yeah, so then thinking about how, if you had an ideal model, tool, systems map, whatever it might be, what might that need to look like in order to best inform the design of interventions? What would be the best use of it to inform interventions? And then trying to close the loop, as it were, to go back and think, and therefore, is there anything we need to think about differently when extracting those models from the interviews or having participatory workshops to build the models, whatever it might be?
Neil, just to dive in and echo what everyone else has said, really, thank you so much for that. That was incredibly informative. And there's a huge amount to take away. I would echo what Sarah said about bridging between the hard and soft aspects of this and the various different disciplines. I guess, and I've said this to a bunch of people a couple of times, but just to reinforce, this is such a huge area in its own right, and there are so many different areas to this. And we've got such an incredible resource with Neil and Jez on the team. I think one of the further challenges, just to add to Sarah, is how do we actually apply this within the resource we have available and in the right way? And what sort of boundaries are we going to be putting to this? How do we align it to the core vision of the project, et cetera, et cetera? So it'd be really interesting to me to see to hear from you guys leading on different sub-work packages, what particular areas you could see this being used within. I know Neil kicked off by saying, written into the bid development, it was within work packages 1, 3, and 4. And whilst that's obviously still on the table and beyond that, possibly work packages 2 as well, we just need to make sure that we go through a process of trying to figure out how we can align resource to what the project needs to be, needs to happen. So yeah, just a plea really, just to hear from people and work package sub-leads on where they would like to see this. And maybe now's not the time because there's been so much information to take in, but I'd be interested to hear from you, Neil, as well, on what you think the best next steps are for that.
Sorry, someone else.
Sorry, so I'm Eleanor. So I will just in just a couple of sentences about Work Package 2. I guess when you were talking, Neil, about unintended consequences and what you call, I can't remember how you call reverse effect. We call it reverse causality. So that's the type of methods that we use in economics are really trying to look at disentangling the causal effects whilst also trying to look at all potential unintended consequences of a policy. And I guess that's what, in your language, what system thinking is. But for us, the issue would be using the big sources of data, how much of all these complex aspects in the system can be actually measured in the resources that we have, and what sorts of kind of variables we can find from what you guys maybe in the more qualitative work highlight as important.
Mm-hmm. Yeah, no, I think those are good points as well. I think there's a lot of the system stuff does actually come from a very quantitative background, but what it hasn't done is it hasn't been very, it hasn't aligned or interacted much with kind of economics or big data, even more recently, in terms of how to extract some of the more quantitative relationships and the processes, the tools, the techniques for understanding and mapping those things that exist within other sciences, in economics and things like that. So I think there is an opportunity to maybe look at those kinds of things where there's alignment and what can be learnt from those models that are more exclusively quantitative. And to get to Dan's point, I think about how we think about this from a kind of project level and what the next steps might be. I think it's something probably it might make sense chronologically maybe to think through. Again, we're going to have to approach it iteratively, but think through a first pass through work pack 1, 2, 3, 4 to think if there's a sort of vague chronology from understanding the problems through to designing interventions and monitoring and evaluating, to start from the data collection and think, what does that mean these systems and models might look like? And then move on to the next work packages and say, okay, does this meet your needs in terms of, would it help to design interventions? If it doesn't, then maybe let's see if we can modify these in some way. If we can't, then what would? And then start from the other angle and then see if we can marry somewhere in the middle of what the modelling might be. I think given that the interviews are kind of coming up, that's probably a good place to start as well to think about.
And could we look at sort of resourcing availability against that? So, you know, I take your point. So sort of scoping out what might be possible in each work package, but could we then, you know, use that to try and understand what sort of resource would be needed to do that all the way through the program and then build backwards from that kind of thing?
I think that's what we'll have to do. Yeah, think about when those needs are going to arise, and you know whether when they overlap, when they can happen sequentially, those kinds of things we need to think about and come up with it.
That sounds good.
Also, just Andy from Work Package 4. So again, just Neil, just thinking about how it could work with this, and that was the public involvement thing. But I can see, just picking up from some of the things you've mentioned, I can see doing participatory mapping with members of the public. I can see how the kind of mental models of how the system works that might generate might look very, very different to the models you might generate from, in quotes, professional stakeholders.
Yeah.
And then that issue about when you'd probably be able to pick up potential conflicts, which might manifest in various kinds of unintended consequences or feedback loops that you'd have to cope with. So I was kind of thinking on a big scale, if you think about France and the Yellow Vest movement, you know, how particular initiatives were implemented and actually you reached a tipping point and people, you get again an unintended consequence, or even more, you know, your Cobra model where you're doing things in certain ways and actually how people interpret that in the real world, in quotes, whatever that is very different to how the people planning the system work. So I could see a really nice and interesting piece of work about participatory mapping with members of the public, identifying different mental frameworks and models and understanding of the systems, and then seeing how that might identify areas of conflict and potential unintended consequences.
Yeah, no, I think that would be really valuable, and there'll be some interesting stuff to do in there. I think the idea that different people have the different mental models and their understanding of how the system works can be, you know, really interesting and important. We definitely found that in kind of the safety critical industries where people are acting in a particular way because they think that a hard physical system that they work with behaves in a particular way. And you see this in scarily in safety critical industries, that people don't necessarily understand how the physical system they're interacting with works. And they have very different models on that. And it can be the same for the planning process or any kind of policy, that if people don't necessarily have a shared model of how things work, then they're all pulling on different, campaigning for different interventions or different levers to be tweaked because they don't necessarily have a shared understanding of how the thing actually works underneath that. And they actually all want the same thing. They may be just using different language, or because they don't have a shared understanding, are suggesting and fighting over different policy levers that ultimately are synergistic or work against each other or all kinds of things. So actually just having techniques to help people to visualize those can be really useful, and that would be a good use of these things, I think.
Yeah, sounds good. Thank you.
Eleonora, I was intrigued by your comment a bit earlier, and I think that would be quite useful to meet up at some point and just see how do you identify from the quantitative data correlations, reverse correlations, or whatever. Where do you get those data and that sort of thing? And I mean, is it things like willingness to pay or accept compensation type curves, price elasticity, those sorts of things you would come up with? And I guess we could have a look and see if people have actually modelled those with system dynamics type modelling before. So I think a discussion around that and just see where those data come from.
Yeah.
I think that would be very useful. I'd be definitely interested in that.
Yeah.
I'm mindful that we've gone over time. Thanks, Neil. That was really helpful for me and
hang on.
for everyone.
I've got a final slide here.
Perfect.
Okay.
There you go.
Fab. Thank you. If anyone has any comments, we can carry it on Yammer or on email. And I think as next steps, it sounds like it might be helpful, Neil, if you come to each of the work package updates. So we've got work package 1, we've got various ones scheduled in, so we'll make sure that you're invited. So, fab. Thank you very much, all.
Very useful, Neil. Thank you so
Great,
much.
thank you. Thank you, Neil.
Thank you. Thanks very much.
Thank you.
Cheers, Neil.
Bye.
Cheers, bye.
Bye.
Bye. Is that all right, Neil?
Yeah, it's all good. Thank you.
Cool.
Great.
That worked really well.
Yeah, it's good.
Yeah.
Trying to work out how I get rid of my slides now. Oh, I see. Okay, right. I'm off now. I'll see you later.
All right then, thanks.
Thanks.
Bye.
Bye.